So in refraction, again, the wavelength shortens, but the frequency stays the same. And what would that mean for the color of the light? Well, if the frequency stays the same, it's going to have the same color. It's just the wavelength that's gonna change. And then with that change in wavelength, the speed changes, right? And so if the wavelength, let's say, gets smaller, uh, the frequency stays the same. The speed of light is going to be smaller. They correspond to each other. Or if the wavelength is longer, the speed of light is going to be faster. So Snell's law is a rearrangement of this setup right here. We have n1 times sine theta 1, n2 times sine theta 2. And so we end up getting n1 times sine theta 1 equals n2 times sine theta 2. What this means is if the normal line here is 0 degrees and we have light coming in at theta 1, the light is going to bend. And we'll see that inside the medium there at theta 2. And we can determine different things, how this light going to bend based on different mediums. So what happens is, let's say n2 has a greater index than n1. That means that the speed of light in n2 is going to be, let's see, if it's greater, it's going to be slower. It's going to have a greater index because n is c over v, right? So if v is slower, then and c stays the same, n is going to be higher. So this could be going from, let's say, like air to water. That would happen. What's going to happen is as light goes, it's going to bend towards the normal line. And we do an example in class where we work through these values. The light bends towards the normal if the index is higher. If the index is lower, it's actually going to bend away, and theta 2 will be bigger. So in other words, the light is going to speed up, and the wavelengths are going to be greater in this case. So let's take a look into this example. Let's say light enters oil from the air at 50 degrees with the normal, and the refracted beam makes an angle of 33 degrees with the normal. And we want to draw the situation and then calculate the index and calculate the speed of light in the oil. So when we draw this out, we'll have the normal line, we'll have the angle coming in, the angle going out, and n1 is air. And so air is very, very close to a vacuum. So when we calculate n as c over v, this value v is very, very close to c. It's like 1.00007 something. It's very, very close to 1. And then oil is what we're going to want to find out here, and we have our two angles. So let's see if you can use Snell's law to calculate this, and then go ahead and calculate the speed of light in the oil as well. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so n1 sine theta 1 equals n2 times sine theta 2. n1 is air, the angle is 50 degrees coming in, and 1 times sine of 50, we divide by the sine of 33, n2 should come out to be 1.407. That's the index of refraction for the second medium, and we can figure out how fast it is. We know the index, we know the speed of light in a vacuum, and so you can see how it slows down considerably here, right? 2.13 times 10 to the 8th. It's still crazy fast, but it's slower, definitely slower than what we see in vacuum. All right, so in this one, light enters water from a layer of oil at an angle of 50 degrees, and oil has a refractive index of 1.65. The water has a refractive index of 1.33, and we want to find out the angle of refraction, and then also the speed of light in oil and in the water. So again, make sure your calculator's in degrees, and remember the inverse function will help you get an angle. Go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. Okay, so we should get 71.87. We're going from a higher index to a lower index, so the angle is going to get greater. And we can get the speed of light in the different mediums. This is for oil, and then this is for water. And so you can see how it slows down almost about half, not quite half. for the speed of light in oil, and then for water we've got that there. All right, so on this one, we've got light entering in a prism, and this one's a little bit more challenging. If you notice here, as it enters, the angle is 0 degrees, so the refractive angle would be 0 degrees. But then when it comes to here, you got to figure out what you think you're going to need to do. So this is a little bit of a challenge, but it's good practice for you here. Go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we've got our incident angle here. We draw our normal lines for incident angle theta 1 would be 30 degrees then. So, if you look at a right triangle, if this is a right angle here, this would be 60 degrees. So therefore, if this is a right angle, this would be 30 degrees here. And we want to find what the refracted angle would be. It would be 50.81, which would look something like this as it goes out. And then part B, what would happen if it's immersed in water? So why don't you go ahead and pause the clip again and give that a try, and when you're ready to check, you can hit play to continue. Okay, so we've got basically, well, we have the same incident angle, 30 degrees, and then we can get the refracted angle, which would be 35.64. So if it was in water, it wouldn't refract nearly as much because the change in speed is not as much.